Hello, listeners. This is Born Curious. We're so happy to be back for season 2, and to those returning, welcome back. And to those who are joining us for the first time, we hope to keep you coming back too. I'm your co-host, Evilise Estrada.
And I am your co-host, Heather Min. Thank you for joining us. Today, we're bringing you an incredibly special episode about a new scientific discovery. Still under wraps at the time of recording, but soon to be published in the scientific journal Nature. To learn more about the fascinating backstory, check out the links in our show notes.
Let's hear from our 4 guests, the experts behind that discovery.
Yes, we're here today with João Alves, a professor of stellar astrophysics at the University of Vienna, Alyssa A. Goodman, the Robert Wheeler Wilson Professor of Applied Astronomy at Harvard University, and a research associate of the Smithsonian Institution, among other things. Ralph Konietzka, a Harvard PhD student in astronomy and astrophysics, and Catherine Zucker, who earned her PhD from Harvard University in 2020 and is now an astrophysicist at the Harvard and Smithsonian Center for Astrophysics.
Welcome all. We're so glad to have you here today sharing this exciting update. And this is the largest number of people on our podcast at once, so it should be a lively one. Welcome. Thank you so much for joining us here on Born Curious. We're here with Alyssa, we're here with Catherine, we're here with Ralph, and we're here with João virtually from Vienna. Alyssa, let me turn first to you and ask you to explain in just a couple of sentences why we're here today and why this is so exciting.
Well, until about 100 years ago, we didn't even know that we lived in the Milky Way galaxy. We didn't know that there were a lot of galaxies. And now we're trying to figure out where exactly we live in the galaxy. And so the Radcliffe Wave that we're here to talk about is the first big feature that we found made of star-forming regions in this local arm of the galaxy. And João, our colleague here, named it the Radcliffe Wave in honor of this institute, but we didn't actually know it was waving. And now we actually know it's waving, which makes it even more unexpected. And so this is really exciting.
Let's get a bit of context. Catherine, as a Harvard grad student, which you are no longer, but in January 2020, you were the second author of a paper in the journal Nature that announced the discovery that rocked the world of astrophysics. Can you tell us what you and João and Alyssa discovered?
Yeah, so what we discovered is essentially the largest coherent gaseous structure that we know of in our Milky Way. It's almost 10,000 light years in length, and it's right in front of our noses. And as Alyssa said, it's giving birth to tens of thousands of baby stars similar to our sun. And so it's really transformed our understanding of how stars form in our local part, in essentially our galactic backyard.
Now, you said that it's in our local arm of the Milky Way. So if we're looking at a map of our galaxy, what does that mean?
So if you look at any images of other galaxies, so a lot of our understanding of what our own galaxy looks like is informed by looking at other galaxies, like tens and tens of millions of light years beyond our Milky Way. And that's because, as Alyssa said, we didn't really know what our galaxy looked like. We didn't even know that we lived in a galaxy called the Milky Way. And so you can sort of, if you look at other galaxies, you can see that there are these sort of spiral pinwheel patterns. Those are called spiral arms. We live near a spiral arm called the local arm. And this gaseous reservoir called the Radcliffe Wave is the densest part of this spiral pinwheel pattern near the sun. And it completely shocked us what it looked like. It should not look like a wave, and it does. And so the question is, why does it look like that, and how is it moving? And that's something that Ralph has been able to tell us.
And also, just to emphasize, Catherine suggested this, but to be totally clear, we do not know what our galaxy looks like. Okay, so part of why this is important is because at least we know what this little tiny piece of our galaxy near us looks like. So we're just guessing from a lot of information that's been accumulated over 100 years that it's spiral-ish. But if you say, like, how many spiral arms does our galaxy have, that's something there's a big fight over. So please don't ask us, because we don't want to get in trouble.
Okay. And João, what questions led to this discovery?
Oh, so this was my Radcliffe project. So we have to propose a project, and this was really, let's see, a year right before the release, the very important release 2 of this satellite called Gaia, that will give us 1 billion positions and proper motions for the stars in our galaxy. And the idea was to test what we thought was the Gould's belt. The Gould's belt is just a ring of star-forming regions where we thought we were somewhere towards the center of this ring, but there were conflicting ideas, models. There were no model really could explain it. It was doing all kinds of interesting things that worked for some models and worked for others. So the idea was to map, using this Gaia data, map the accurate distances, understand the structure of this Gould belt that turns out does not exist. There's no such thing as a Gould belt. Instead, there's this Radcliffe wave.
This Gould belt was first proposed in the late 1800s. And so this was the prevailing structure in our galactic backyard for over 100 years. And so what we'll talk about today is the Radcliffe Wave, which is the new structure that's overturned this Gould's belt that Joao was talking about.
So if we could skip to you, Alyssa. We had heard a great story about Indian food in your office that was a part of this discovery and revelation. Can you share that with us briefly?
That is a true story. And the fuller story is that Catherine, as you said, who is now a Smithsonian researcher, was a graduate student then. And she spent a lot of time not just at the Center for Astrophysics, but here at Radcliffe with Joao in his office, in the blue carpet building, as she calls Byerly Hall.
Very nice, very
beautiful
nice
blue carpeting. Fantastic espresso. But anyway, so she would come visit all the time with Joao. And so she saw Joao more than I did, and she did a huge amount of work on this project. And so they knew things I didn't know. And they got to the point where they had a big structure. It wasn't quite a wave, actually. It was sort of a wave and a half. 1.5 periods of a wave at that point. But anyway, they had this thing, and I hadn't seen it, and Joao was all excited. And so on some Friday afternoon, quite late, he called me, and Catherine wasn't with him, and he called me and said, "Where are you?" And I said, "Oh, I'm in my office at the CFA." And he said, "Can I come by?" And I said, "Well, it's almost dinner time." And he said, "Yeah, but I have something great to show you." And his family was out, and I didn't have any plans, and he's like, "Let's get dinner." And so we were planned to order Indian food, and then we realized we cannot leave Catherine, who's the linchpin of this project, out of this offer of Indian food. So we call Catherine, and she says, "Of course I'll come over." So she comes over, and we order Indian food, and we're sitting there, and we're looking at the data, and he's showing me what he and Catherine had been working on, and there was this beautiful line of dots that looked like it was forming most of a wave, and we were looking at it in GLUE, which is a visualization program that we all use and rely on for this. And at one point we said, wow, that looks great. I wonder where that is, like relative to the galactic plane and where we think the arm of the galaxy is. And I very foolishly said, if only there was some software that we could just put this all into context. And then I remembered that in GLUE, we have this plugin for something called Worldwide Telescope, which does exactly that. So anyway, you can, in this program, you can just drag the data onto the viewer for Worldwide Telescope, and the three of us were sitting there looking at it, and they had all, seen how interesting it looked on its own as a structure. But then when we saw how it looked in the context of the galaxy, I think none of the three of us will ever forget going, "Oh my goodness." and because it lined up with where people thought, it turns out to be slightly not the local arm, but anyway, an arm of the galaxy is, and some dark lanes in a cartoon model just by accident, okay? And all the dots fit in the cartoon model, and then you could turn it sideways, and you could see that it was coming way out of the plane. And like I said, at that point, we were going to call it the local femur, Joao, right? We didn't know about the rest of the wave. There's a whole other...
The monolithic femur.
The monolithic femur, yeah. Anyway, it turns out that we ourselves, good scientists don't believe crazy things initially, right? So we had to keep checking and checking and checking. And so one of the things that Catherine and Joao did after that was just see how far it could be extended. Anyway, we had to sort of fill in this pattern, and the eventual filling in was after the Indian food story. But the Indian food story was enough to be pretty exciting.
So that was the first time that you all just saw
together.
Yeah.
I mean, there had been lots of. I think Joao should and Catherine should weigh in on this. But there had been lots of, kind of almost getting better. But that was the first time I think that we saw it in the context of a view of the galaxy, a fake view of the galaxy, an estimated, data-driven view of the galaxy, but fake.
So thank you for all of that wonderful context for why we are here in February 2024. So, big announcement is happening. Let's bring in Ralph, who is the lead author on the paper published today in the journal Nature. You are a relative newcomer to this story, but an important one. Your colleagues have described this new chapter of the Radcliffe Wave discoveries as a triumph of Ralph's data science. Tell us about your data science.
When we started this project, we had this wonderful catalog of all the big, gigantic clouds in the solar neighborhood. And when we were working around with their positions, we got more and more information about the little baby stars forming in the clouds. And for these baby stars, we know their positions, we also know their velocities. So we know for the first time had not only a three-dimensional, just position-based data set as the space which surrounds us here in this room, we also had a three-dimensional kinematic data set. So the main data scientific question was, how can we combine the three-dimensional positions together with the three-dimensional velocities to get a full kinematic picture of the Milky Way.
And kinematic is velocity?
Exactly. Kinematic means the velocity of the stars. But that was not only it.
They're moving.
They're moving, but the question was, how can we connect their motion with their positions in a physical meaning sense? And one of the big questions there was, how can we model the force which is pulling us here down on Earth, which makes us sitting here on this table, which acts between the stars, the so-called gravitational acceleration between clouds, between stars. The same force which makes the Earth rotate around the solar system makes also the stars in our local neighborhood move within the galaxy and through our basically neighborhood.
Because they're not moving just erratically. There are rules and bounds and predictable patterns?
Exactly. And these rules needed to be analyzed and modeled precisely that we can predict how the stars move in the future and where they were born in their beginning. And with the implementation of those rules, we finally could trace also back the birthplace of these little stars, the big, gigantic molecular clouds, which gave rise for the Radcliffe Wave at the first place in 2020.
So why should mere mortals, people who are going about their busy day listening to this podcast, care about the latest discoveries about the Radcliffe Wave? Joao.
Me? Okay.
Do you want to take a shot?
Sure. I mean, the point of the paper, of Ralph's paper, was exactly to prove that the wave, the Radcliffe Wave, is oscillating like a wave. Now, why do you care about that? It allows you to figure out where the rate, once you know how it oscillates, how it was oscillating in the past. And we know the motion of the sun, so we can go back in time and see what happened between the Radcliffe Wave and us, the sun.
Are you saying it gives us clues as the origins of...
It gives us clues of the environment we have been going through, the solar system, we've been going through since the formation of the solar system. It gives us clues how are we part of the Milky Way? And we tend to think, well, there's the Milky Way and then there's the solar system. It turns out they vary, you cannot separate them very, very easily. You are constantly interacting with the Milky Way. And this story we don't know. We're just beginning to unveil this part of blood.
It's as if we were living in a little dark room, and we opened the window on one side, and there was this gigantic gaseous structure right next to us that had this huge wave in it, and we called it the Radcliffe Wave, but our fingers were crossed behind our back that it was actually waving, and now this picture has a moving component to it, and the Radcliffe Wave is actually waving. So it was a good name after all, and we didn't originally know it was even there, and now it's there essentially waving at us.
When I was in kindergarten, I was told how is the neighborhood inside the solar system looking like. So there are planets, there are some meteors, there's some asteroids, but nobody told me anything about how are these planets moving. And when I finally got to high school, I was told, oh, the planets are surrounding the sun, and there is the Kuiper belt or the Oort cloud with even more material around the solar system. But what about the galaxy? What about the Milky Way? How does that look like? When I entered university, Then I got to know the Radcliffe Wave, how the neighborhood of the solar system in a galactic context looks like. So I could look out of the window even further and learn more about how our environment really is shaped and formed. But the question was, like with the planets, how is the neighborhood of the solar system in a galactic context moving? Is the wave static? Are the planets static? And then we found in this work, no, the Radcliffe Wave is moving and it's oscillating like a traveling wave.
A few years ago, right, when the Radcliffe Wave was first discovered, we thought it was pretty amazing, kind of what Ralph was saying, to have a static picture of where things were around us, right? And then what's happened since then, with this discovery and a few others, is you kind of turned on time, and then it's a movie instead of a static image. And in that movie, the Radcliffe Wave is waving.
But even like more generally, if you want to sell your science to the funding agencies, the question that they want to know is, how do stars like our sun, how do they form in galaxies like the Milky Way? And so, like, the initial discovery of the Radcliffe Wave, it showed us that all of these star-forming regions were connected on such a large scale that we never knew before. But then what Ralph has shown us is that they're all moving in a coherent way. And it's showing us that star formation itself is very dynamic. These clouds likely live and die on short time scales. Like, this wave is likely not to last a long time. Like, we've passed through the Radcliffe Wave 13 or 14 million years ago. But because of the dynamic nature of star formation in our galaxy, like 14 million years in the future, the neighborhood we left behind is going to look very different. And so it's this dynamic story. It's a dynamic moving picture of our galaxy. And that's why we care about the Radcliffe Wave and why we care about Ralph's Nature paper out today.
Let me say one thing.
Great
So,
answers.
yeah. So this Radcliffe Wave is one such wave, the one that we've observed. But there are any number of waves out there in the universe. That's what we're saying, right? So there are many, many of these waves that are making many, many more baby stars.
Yes, we think.
So the stars are moving,
Yes.
they're moving, and they're waving.
And
At
now
the same time.
Yeah, and now the excitement comes in when we now had this data set about the stars. We saw the wave is not even just looking like a wave, it's behaving like a wave. Because the stars showed us that the Radcliffe Wave is oscillating through the galactic plane, and the oscillation is most consistent with a so-called traveling wave.
So it's like we're sitting in Fenway Park and all the fans are doing the. Is it comparable to that? Is
That's
that what
exactly
you mean by
comparable to that.
oscillation?
Imagine you sit in Fenway Park and every little fan is a little star in our local neighborhood. And when the star is moving upwards out of the galactic plane of the Milky Way, it's the same as one of the fans is jumping upwards. And if you have several fans in a line jumping upwards at the right time, the same is happening in the Milky Way, where little stars are jumping upwards at the right time and then pulled backwards by this gravitational force, such that we see this wonderful pattern called a traveling wave moving through our local neighborhood.
That's awesome.
It may or may not be a detail, but I feel like we should just say one more thing, which is that you just said, Evelise, that the stars are moving and then waving. It's not quite that simple. And Ralph's triumph is actually of physics and some data science, but importantly, some people in Joao's group provided a very key piece of this story. And so the story is that if you try to measure the three-dimensional velocity using kinematic tracers that Ralph was talking about of individual stars, they are a little drunk, okay? It's not like, oh yes, I'm going to go away. It's that you can use those motions and you can use this information about where they are near these big clouds of gas that are presumably forming these stars to make clusters. And then once you have those clusters, you can use the bulk velocity of those clusters, okay, to see this motion that we're talking about. And so it's really as if we could take the clouds that Catherine and Joao placed along the wave and use the stars as little proxies for their motion, and then the clustering of those stars really as the proxies. And again, even with the clusters, the motion is astonishingly well fit by a traveling wave. I mean, the figures in Ralph's paper show you that. But again, if you did it with the individual stars, it would be hard, and you can ask Ralph and Joao to pull out that pattern.
Maybe just to add one thing. So this
Yes,
was
please.
really important, what Ralph did, because we were asked, Catherine, Alyssa, remember, one of the referees of our 2020 paper said, how do we know this is a wave? We have to prove it's a wave, and we really didn't have the data at that point. So we passed, so the referee let us go, but it was on us to prove that it was indeed oscillating. It looks like a wave, but we want to know that, the top part comes down, the down comes up. And this is what Ralph did. And so this is why it's a very important achievement.
So it's an oscillating wave. What is the significance of this?
I think it's, as Alyssa already said, 4 years ago, it was the first time we saw how the local arm of the Milky Way looked in 3D. And now for the first time, we see a spiral arm-like structure, not only how it's lying there in the galaxy, but also how it's moving in the galaxy. And just having a straight line, which was already the picture of these spiral arms in a plane, is totally different as what we are seeing now, as of a spine-like structure moving upwards and downwards through the plane. And not only that, but also continue doing that through this traveling oscillation. So it keeps on moving and is not static in space with a constant offset, basically. And maybe that's a little bit too detailed already, but with this this observation of this traveling wave, we were also able to constrain backwards how strong the gravitational force in our Milky Way is. So we now know how the local neighborhood is not only looking, but also how it's moving. And with that, we could constrain how strong the pullback on all these little baby stars is. So how strong is basically the force who keeps the fan in a stadium pulled back to the seat.
In their seats, yeah.
I've got another metaphor, which is maybe crazy, but I'm picturing an octopus, right? And the way it moves the bottom of the ocean with all its arms kind of
Cool, yeah.
And so I'm picturing our galaxy.
Wow, is it too late? The Radcliffe octopus? No, it's a little too many arms there.
Too many arms.
I do really like the ocean analogy, though. So it's really hard. We don't see a lot of examples of traveling waves in real life. So one of them is actually light, but obviously it's hard to see that, to slow it down enough to see it. But waves traveling over an open ocean is a pretty good analogy. It's not perfect, but it's pretty good. And you can think of these baby stars as sort of buoys. And so as this gaseous structure, as these ocean waves travel up and down and they bob up and down, the buoys are bobbing up and down with them, and those are the baby stars. And so that's what Ralph has done, is he's used these baby stars to trace the motion of the gas.
And there's another question that gets to your other question about the significance of this, which is we made this video where I basically tortured Ralph and Catherine to go outside with this red rope and shake it so that it would make a traveling wave, because it's important to understand the difference between a standing wave, where the rope would just go up and down, and a traveling wave where you put a pulse down the. But it's important for the referees. It may not be important for the public. But anyway, the thing that you could object to as an analogy is whether or not the regions know about each other. In other words, this thing moves as a coherent structure, but it probably just appears to move as a coherent structure because of the gravitational pull on it, okay? And because of the way the gravity is arranged in the galaxy, the mass is arranged. But it's also interesting to think well, actually, are they connected, by a magnetic field, for example? Okay, we do not know the answers to those questions, okay? But it's an interesting question. And so even just thinking of these analogies makes you think more. But getting back to your, why does this matter? To me, another reason that it matters is, in my own career, I've gone from studying in Chihuahua to very little things that form individual stars, to bigger clouds that form a lot of stars, to now how are those clouds arranged in the galaxy? And the littler the thing you care about, the less the rest of astronomy cares about what you're doing, okay? and we finally now have gotten to the scale where we're saying something about how the distribution of gas in galaxies gets turned into stars on the scale of a galaxy. And so that then it very much has an impact on how galaxies themselves change over the lifetime of the universe, how they form stars, which changes their color and their appearance. over many, many cycles of star formation. Just to give you the idea, the oscillation period of this wave is about 90 million years. Okay, so it would do this, you know. And so when you look at the animation, you'll see that the little star cluster animation pieces disappear because we don't think those will last more than, I don't know, 10, 15, 20 million years, okay? Maybe less, okay? And so they disappear because this pattern could persist, but the actual stars forming will not, okay? So that 10 million years, say, is a total flash in the lifetime of a galaxy, which, you know, is whatever, 14 billion years, something like that, and the age of the universe being a little bit more than that, okay? And so there's a lot of all this going on in the history of any galaxy, but it's only our galaxy where we can see up close what's going on. And so the real trick for the next step in all of this is to figure out how much of this is going on beyond what we can see locally in the Radcliffe Wave, and then how much of it is going on in other galaxies, and then how does that matter in galaxy evolution and the evolution of the universe. So we've finally gotten to the point where, you know, what used to be local studies of star formation now impact the structure and evolution of galaxies and the universe. So I think that's really fun.
And I think one important point is also to find out what is the origin of these structures. So was there a big clump of mass falling into our galaxy and make the entire structure and the entire plane wiggling, such should we observe these waves today? Or was the origin of the wave more in the plane located? So were there stars exploding in our neighborhood so heavily that they push the gas out of the plane? So the star is exploding, the fan in the stadium says, hooray, jumps up, and the stars are basically moving out of the plane, or better to say, they're birthplaces, the molecular clouds in which then the stars formed once they are pushed out of the plane. So these are just two scenarios, and we now need to try to rule out or basically focus on one of these scenarios to say, this gives rise to these structures, this gives rise to this kind of patterns we see, and is the same formation process not only possible in our local neighborhood, is it possible in other places in the Milky Way, or might it even be possible in other galaxies? So are all the galactic disks, not even in the Milky Way, but also in the galaxies we observe, wiggling and pattern as we see it in the local neighborhood?
I'm very curious to ask Joao what his favored theory for the origin of the Radcliffe Wave is. Joao, do you have any ideas?
You have to go on the record.
I have a
on the
favorite
record.
one, but I know it's wrong.
That's okay.
Should I tell it?
That's totally
Yeah,
okay.
What's the
we would
favorite
love
wrong
to
one?
hear it.
I have a
So
new
what-
favorite wrong one, but go ahead.
Okay. So this, so there is. We know that the galaxy is accreting, is gaining mass from the intergalactic medium, and there's a halo around the Milky Way, and of gas. And you could imagine that the Radcliffe Wave, because it would explain a lot of things except some fundamental ones. If you have a clump coming through and hitting the plane of the Milky Way, it will do exactly what you would expect to do. So you go, okay, so on the Milky Way, it works like this. If this is a plane, if you're here, if you're a person and you're here, you will be pulled down to the floor, but the floor doesn't exist. So you go down the floor, and then you realize, oh, I have to go up again. And you go down and up again, okay? So if you have gas plunging on the Milky Way, it will go down, and then it will go like, oh, I have to go up, because they're pulling me up there, and I go up. And there's my wave. And that wave is actually attenuated, because unlike stars, the gas loses energy when it does this. That will be perfect. Now, the fundamental problem with this is that what are the chances of this gas arriving at the Milky Way at the same velocity as the gas in the Milky Way is rotating around the plane? And it's very unlikely that to be the case, but we don't find that. So the velocity of the Radcliffe Wave fits very well in the overall pattern of rotation of the Milky Way, the local Milky Way. So that's my favorite, but it's wrong.
Although it would be very significant because we haven't touched on, there are a lot of people now, including in our wider collaboration, who are very interested in the interaction of the stuff in this halo and these so-called streams of stuff that, are way out of the disk of the galaxy, and how does that interact with what's going on in the disk of the galaxy. And I'd give it at least a 50% chance that the Radcliffe Wave has something to do with that, okay? Not exactly what Joao said, but the other 50% is what Ralph said, which is that it's entirely driven from things that are happening inside the galaxy.
I wish that we could take all of the gas clouds in the Milky Way and we could truly, perfectly, very precisely figure out exactly where they were 50 million years ago and 50 million years in the future. And so we have proxies for that, but it's never perfect. But if you have a simulation, so a computer simulation run on a computer, you essentially feel like God in the sense that you can control how things happen. You can turn on and off gravity. I can turn on and off the magnetic fields that Joao made this face at. I can explode supernovae in these simulations. And by me, I mean my favorite simulator friends. And so I have a number of collaborators. We have a number of collaborators that have been running simulations of galaxies like the Milky Way and trying to figure out whether we can find structures that look like the Radcliffe Wave. And if we do, how did they come to be? How long will they survive? What will they be in the future? And so my favorite sort of key origin theory is that it's very tied to supernova explosions. So Ralph mentioned this, but there has to be some way to get the gas out of this pancake-like disk of our galaxy. And so you have to have a powerful force to sort of counteract gravity, which wants to keep everything in the disk of our galaxy. And so if you explode a bunch of massive stars, you can push that gas up and then naturally it'll fall back down. So there is some details involved, but I'm going with the supernova theory.
I would even say that simulations even started the entire Radcliffe Wave story for me, because when the original discovery paper came out in 2020, I was still located in Munich and started on my bachelor thesis. And my advisor and mentor back there, Andreas Burkhardt, told me, look, there is this wonderful work about the discovery of the Radcliffe Wave. Why don't we look in simulations if we can throw different massive clumps into the Milky Way if we produce these patterns? And then we showed that it's unfortunately very unlikely that these clumps throwing or flying into the Milky Way are able to produce the right wavelength and the right structure size comparable to what we see in our local neighborhood.
The right answer is probably that it's very complicated. But from Ralph mentioning Andy Burkhardt, we should also say that there's 4 of us here, but there are a lot more people involved in this project, and there were a lot more, including Andy, who were interested in and involved with the original Radcliffe Wave. So yeah.
Around the world.
Around the world.
And at all levels of science. So students all the way up to...
Yeah, did we mention that Ralph is a first-year graduate student doing this work?
Extraordinary.
Exactly.
So we've been talking about simulations, kinematic data, science, glue, all sorts of software projects, as well as the Gaia satellite. So what would you say were the scientific and data breakthroughs that made these discoveries possible in the last 4 or 5 years?
So the most obvious one is, of course, the Gaia data. The Gaia data is one of those things that for people working on the Milky Way and stellar astrophysics, there's a before Gaia and an after Gaia world. So Gaia is completely changing, transforming the field. I think that's probably number one. But as important, you can have all this wonderful data, but if you don't know what to do with it, it's just a pile of a lot of data. So I think what's very important here was the models on which, the dust models that Catherine was working on, that made all the difference in determine high accuracy distances to these clouds. And to give you an idea, I mean, all the clouds have been there since 1870, whatever, even before that.
I think they've been there for a lot longer than that.
A couple of years before that, if I remember well. And, we've been looking at them. I've been looking at them. Alicia have been looking at them since we were babies, and we didn't realize what's in front of what. And so the trick was really the right data and the right method. And the method was the method that Catherine was working on.
It's 3D dust mapping is what.
And I'll never forget that, the time that Joao and I spent in his fancy office at Radcliffe, where he would be like, Catherine, look at this region, look at this stellar nursery. I predict it's at this distance because this would help me form this wave. And I was like, I don't know, Joao. And then we looked at it and I was like,
No, yeah, Catherine was not a believer in the very beginning,
Yeah.
but
Once we got halfway reconstructed, though, then I was on board, and I was
Totally
excited
on board.
Yeah, so we should probably mention Doug Finkbeiner, who's another professor here at Harvard. And
Yeah.
it was his group really who pioneered this technique of 3D dust mapping, which we can get into if you want. But let's just say that it uses information from Gaia, which is about stars, but to actually measure the positions of these gaseous clouds. And you'll hear us interchange, call it gas clouds, molecular clouds, dust clouds. They're all the same thing. If you want to know why, we can tell you why, but they're all the same thing. And so what Joao is saying is that when he and I were, as he put it, babies, it was very hard to estimate the distances to any of these things, because this is when you see beautiful pictures of astronomy, they're often nebulae, and there's often sort of these dark, smudgy stuff and this bright, glowy stuff. Those are called dark nebulae and bright nebulae. And so these molecular clouds, dark clouds, dust clouds, what do we have called them?
Stellar
Other things.
nurseries.
Stellar nurseries. They're all the same thing. They're all they're like these nebulae that you see in the pictures. And it's the dark stuff that's the dense dust that's forming stars in the future. And that's the stuff that he and I have had many colleagues tell us are at a whole variety of different distances. And then what happened with even just the second release of the Gaia data is these techniques that Doug his students had been working on for a decade suddenly became much, much more accurate. And so
just,
Catherine.
yeah, and just to give you a sense, I was working on this with another PhD student in Doug Finkbeiner's group. His name is Josh Spiegel. And essentially the 3D dust mapping pipeline that we built together, it improved our understanding of where these stellar nurseries were by a factor of 10, essentially overnight. So I think we all, at least I know Joao and I remember the exact dates that this Gaia data was released. And so 3D dust mapping, before that date and after that date, it changed in a revolutionary way.
And it's changed since, because
Yeah.
there's been subsequent data releases, more improvements to the algorithm. And now, a lot of Catherine's work since the Radcliffe Wave, which we've been privileged to also be involved with, but shows you the structure of individual clouds and then their arrangement in 3D. And so, that's not what we're here to talk about today, but you should just know that this being able to find the distance to an individual cloud, we thought that was a great triumph, but that's nothing compared to what we can actually do today in terms of actually telling you what the shape of these regions are in 3D. And this is just something I never, ever thought I would see in my lifetime. And so it's I cannot describe how fun and amazing this is.
Wow. And the Radcliffe Wave is part of that. So the Radcliffe Wave has
Step one.
changed our understanding of our galaxy and our place in it.
Absolutely.
And it sounds like there's a lot more still to discover about the Radcliffe Wave. Can we talk about that, Joao?
No,
It's a secret.
it's top secret. So I think the origin, as Ralph mentioned, is probably what's on our minds most of the times. Because if we know how to form Radcliffe waves, and the simulators kind of know how to form them, but they have no clue why they're there. They just show up. But it just tells you how complex of a problem it is. So they do these very, very complex simulations and, let them run, and then the magic happens. And they do see what we think are the equivalents of Radcliffe waves in the simulations. So this is clearly something that we'll need to work on, and we are working on. Other things that might be fundamental for us is understanding how stars form. And we always think of, when we talk about star formation, we always talk about, well, there's the molecular cloud, the mother cloud, and then the baby stars formed. But no one ever talks about how do you form the mother? Mm-hmm. So how do you get to the mother, right? We are very interested about that topic here in Vienna. And we finally have a way to figure out, this is how mothers are formed. And then eventually baby stars are formed too. But that's, for me, probably one of the most exciting ones.
Also, when I said it's probably complicated, one of the simulations that Catherine has been working on with Sarah Loebman, who's one of the people who do these simulations, shows something very counterintuitive, like that you wouldn't guess. And so if you see a picture of an actual external galaxy, and you see it now as a snapshot in time, and then you think, well, where is the gas or stuff, okay, that was in one of these spiral arms, say 100 million years ago, okay, again, which is a short period of time in the life of a galaxy. Well, you would think like maybe there's a galaxy and it's kind of turning, and so maybe the arm just kind of moved. And no, but the simulation actually shows that the gas in something that would look vaguely like the Radcliffe Wave actually comes from like very far away in the galaxy, and that the structure kind of coalesces and changes and turns. And so for me, I have a very big interest in data visualization. And so I like seeing these simulations where they can trace back where did the gas in the simulation come from, and that could maybe give us hints, because what Joao is suggesting is it's not as simple as some supernovae go off and stuff goes up and stuff goes down, or something comes in from outside and hits it. Okay, if it was that simple, we would have figured it out by now. Okay, so it's some combination of something maybe comes in, maybe there's some supernovae, the galaxy is rotating, there's stuff called shear, God forbid magnetic fields. Okay, but there's like all of these processes acting together over these timescales. And so the simulations may give us the best hope of what to look for to sort of distinguish between these scenarios. And yeah, I have a toy in my office that I was playing with last week. It's called Galileo's pendulum. So it looks like Newton's cradle, the thing where you take a ball and but this one they're all different lengths, the strings, okay? And you can actually make a beautiful traveling wave when you use this thing. So I came up with this crazy idea about like you could have an inclined shock wave that presses down on the galaxy from outside, and for reasons I could show you in a cartoon, would actually cause this wave. But Ralph, our great physicist, says, no, this would only work if you had a gradient in the gravity and the velocities that was consistent with the wave being like sideways, essentially, not along an arm, but perpendicular to an arm. And then I remembered the simulation. I said, but look here, you could have it like this. But you understand, this is the stage we're at. We're just making stuff up and trying to sort of test it out. And then Ralph is very realistic and very tied to physics.
He knows the rules of the universe.
He does.
Ralph,
and it sometimes is very
honest,
disappointing.
is what I like to say.
But no, I mean, my guess is that it's a combination of things, and there probably is one dominant process, but we don't know what it is. And I certainly would say that this is probably not the only case of this happening. And that one of the tricks is going to be to find out how often it happens, and also what it has to do with these huge cavities like the local bubble that Catherine has been leading a lot of studies of. And so the local bubble is this huge cavity that we knew about around the sun, but we didn't know that all these star-forming regions are on its surface, and some of those star-forming regions are in the Radcliffe Wave. And so the local bubble does matter in this conversation in that it touches the Radcliffe Wave. It probably doesn't generate the motion of the Radcliffe Wave, but so we have these, it's like having a puzzle, it really is, with just a few pieces filled in. So we had no pieces before, and now we have like a few pieces, but we have no idea what the pieces look like out here. But, is it a repeating pattern? I don't know. Is this some weird region we happen to live in? You never want to assume that.
No, the
Right.
Copernican principle tells us that
No,
we
don't do
cannot.
that.
Unfortunately, we're not.
Right.
We're not.
But
that
we don't have the
special.
other pieces.
I'm sorry.
Maybe we even need to change our view to external galaxies to see entire galaxies from top down, and if we can discover structures which are similar to the Radcliffe Wave there. Because in this sample galaxy, we could study the entire region, what's not possible for our own neighborhood, where we only see the first 10 to 20% of the entire Milky Way. But for external galaxies, where we see the entire, basically, planar disk, we might be able to discover patterns coming towards or going away from us, which are so similar to the wave that we can learn from their origin how the local neighborhood of the solar system might be formed a couple of million
We
years
should
ago.
explain, because it sounds like magic, but we actually do have ways to measure the velocity of material coming toward or away from us in external galaxies. For stars, very poorly. For gas, pretty well. And the resolution, so the sharpness of the images of external galaxies, has gotten tremendously better with instruments like ALMA and JWST, James Webb Space Telescope, in the last 5 years or so. And so what Ralph is talking about, again, would have been almost impossible a decade ago, and should be very possible in the coming decade. And I would put my money on that as a easier way to figure this out. That plus simulations.
Okay.
Yeah.
I want to back up a little bit, Alyssa, because you mentioned that Ralph is a first-year graduate student. Catherine, you were a PhD student when you did this work in 2020. So beyond the scientific the wonder of the scientific discovery, there's a really beautiful story about the role of students in scientific discovery. Can we talk a little bit about students' role in this type of work?
Sure. I mean, Joao had been working on methods to measure the distribution of stuff in 2D. Okay, this black stuff we're talking about in images for years. And Doug Finkbeiner had been working on this technique with his students to do this 3D dust mapping. And they didn't actually know each other. And I knew both of them, and I just always thought this was astonishing. And so part of the reason I think Joao was excited to come here for his Radcliffe Fellowship is that he could work with Doug's group. And so Catherine was the connection between Doug's group and Joao, and obviously they became very close collaborators, way more than, so Catherine should explain that. And so, it was this sort of perfect confluence of Joao comes to Radcliffe. Catherine had started working with Doug in addition to me because I went on sabbatical, which also had to do with the Radcliffe thing, but never mind. And so Catherine had become expert on this technique, and she spent a lot of time having coffee in the blue carpet building and measuring distances to these clouds. And then like Ralph said, his undergraduate advisor, Andy Burkert, is a close friend and collaborator of ours. And so, of course, I don't know, did Andy actually give you the paper, or you found it on your own?
No, Andy gave me
the paper, right? And so Andy's also an excellent mentor. He's in Munich, in Garching. And anyway, so, right, so he involved Ralph. And I was, again, on sabbatical in 2022 when Andy contacted Catherine and Joao and I and said, there's this undergraduate student. I have to introduce you. He's working on the right. I'm like, Andy, I'm on sabbatical. No, you have to meet him. And so we met Ralph on Zoom. And then a few months later, he was here and he became part of our enterprise. And we decided he was indispensable. And he shocked Andy and Joao and me by saying he wanted to apply to Harvard for graduate school. We thought he wanted to stay in Europe and that the hard choice was whether he was going to be in Vienna or Munich. Of course, he was admitted, and then he miraculously came here. And so he continued pursuing this Radcliffe Wave motion project in collaboration with all of us. And he had been working, he could tell you more, but on this before, because Joao and Andy and I and Catherine are friends. And this is what's great about astronomy. It's a very small field, and most people in it are very nice. And so if you work on a specific subject, you get to know the people in that field, and some of them become your close friends. And then, like that Indian food story, it's like the three of us are friends. Like, we were just having a great time. And by the way, look at that. It's the largest known gaseous structure in the universe. And anyway, so it's really kind of a social network, if you will, how these people come into these collaborations. And then, there's something about Harvard, which is pretty charmed in terms of how fabulous the students that we can get here are. And actually, Catherine and I met when she was an undergraduate also, and she was like Ralph, a spectacular undergraduate who I had gotten to work with on research and who I begged to come to Harvard. And as they say, the rest is history.
So I guess what Alyssa is trying to say is there will be no Radcliffe without students.
Radcliffe
Wave, sorry. Radcliffe Wave.
Absolutely.
And all of you talking to each other, you're not like a lone genius in a corner by yourself. You actually have to talk to each other and exchange ideas and theories and say, no, not so much, or, that.
Absolutely. But if it was just Joao and Andy and I talking to each other, this would not have happened. In other words, the students are the ones who have the most time to think and the most ability to, use what they've recently learned and apply it and focus and be smarter than us. Yeah.
They're the spark. You're the spark. Sounds like
they're the spark and the actual execution. Yeah. Somebody. Yeah.
Okay, we're winding down at the home stretch here. So this is a question for all of you, really open-ended. Is there anything you care to add to this conversation that we have not yet talked about? Let's start with you, Ralph.
We could start with the whole dark matter idea, but I think that goes too far. Or shall we?
If
Go
it's
ahead.
critical.
It's
I think
interesting.
I think it's a good one.
It's very interesting.
As I already started to explain a little earlier, with the Radcliffe wave being a traveling wave, it gives us a tool to measure the gravitational pull of our galactic neighborhood. So how strong are the baby stars and the big molecular cloud are pulled back to the galactic plane, are going through the plane and then pulled upwards again. And the question now is, if we measure the strength of this galactic pull, what can we say about the dark matter in the solar neighborhood? And when we observe all the matter around us, which is radiating normal radiation, so the same radiation we are able to see with our eyes, then we get a constraint on the visible mass in our solar neighborhood. But there is also a different component, the so-called dark matter, the dark mass component. And comparing the visible mass, or what we observe with our eyes, with the gravitational pull, and taking to some extent the difference of the two, we can obtain a measurement of the dark matter in the local neighborhood. And with that, we were finally able to say that a theory proposed around 8 years ago, that in the solar neighborhood or next to the solar system, there is a really thin disk of dark matter, that this theory is really unlikely to happen, and that all the dark matter is more collected in a big halo surrounding the entire galaxy.
Yeah.
There was a beautiful plot in the paper that we were ultimately asked to remove because it was too far from the central point of the paper. But what Ralph's not telling you is that this theory was proposed as a way to kill off the dinosaurs. So seriously, there would be, if we passed through the Earth and the Sun, passed through this clump of dark matter, it could attract more comets, and then the comets would hit Earth, and then they would kill the dinosaurs. And so there was the whole book, and it's actually about somebody here at Harvard, written by somebody here at Harvard, but it was about dark matter and the dinosaurs. Anyway, and so there was a big controversy about whether or not this was true. And so Ralph had this great graph that had a little dinosaur on the axis. But anyway, it's not in the paper now.
So we've moved through this band of dark matter before.
Well,
potentially.
no, it doesn't necessarily exist,
Okay.
is the problem. The theory would be that, yes, if we had moved through something, it would change the gravity around the Earth, which would
Okay.
Attract extra things hitting the Earth. Yeah.
Could the Radcliffe Wave come this way
What do you mean?
through our solar system?
Oh boy, that's
Yep,
a
that-
whole other story. Go ahead,
Wow,
Joao.
that's for you.
Okay, so that's the top secret. I'm not allowed
Yeah.
to talk about it. No, I'm joking. So the most fantastic thing that I think is that we, the solar system, planet Earth, were inside the Radcliffe Wave. We crossed it, and we learned that about 14 million years ago, that happened. And we don't know exactly what that represented yet on the geological record. But there are interesting events that happened 14 million years ago on the geological record that could be related to this passage. What's exciting about it is that we're realizing now, because we know the motion of the gas, and we didn't before, is that we can do this back and forth. We can go into the future, can go to the past. And we're kind of realizing that the sun must have been inside clouds much more often than we used to think. So I think this is very, very new. It's something that we are just about to submit the paper on. And you'll hear more, hopefully, in the future.
And one thing that Joao didn't mention, and that Ralph didn't mention either, is in his paper, the sexy motion everybody cares about is the oscillation, but he also measured the drift of the Radcliffe Wave. And so, Ralph, you want to say what that is and why it matters to this story?
All the motion we are not talking about is perpendicular to the galactic plane.
Up and down.
Exactly.
Up and down.
But we also see the wave drifting within the plane away from the solar system or away from the galactic center. So we see this pattern which is moving not only vertically up and down, but also moving totally away from us. And now we can speculate that probably this tangential motion in the plane might be connected to the origin of the structure. Alyssa already mentioned earlier, gas was swept up in the first place to form this really straight filament, and then through an additional process pushed out of the galactic plane such that we see this oscillation today.
And so just to explain a little bit more, from the top down, the Radcliffe Wave doesn't look like a wave at all. It looks extremely straight, unexpectedly straight. And so anyway, there's a whole moving picture to be made of the interaction of the Radcliffe Wave with the local bubble and the sun and a bunch of small clouds. And these are other results that you'll hear coming from Catherine's world, from Joao's world, from Ralph in the future. So there's this world where you can have the density and velocity of things that are stars and gas all measured together just lets you ask all kinds of questions that are interesting, and that honestly, things like what clouds did the sun go through, and what do you like to call it, Joao? Is it interstellar weather or galactic weather?
Galactic weather.
Galactic weather. Like, that was not something that I thought about a lot.
So many variables in the galaxy are always moving and changing.
I mean, this has been touched upon sort of very briefly, but everything we've talked about in this entire podcast is taken place in a tiny fraction of a much larger Milky Way. So something like 10% of the entire size of the galaxy. Mm-hmm. And so these are big ideas that we're presenting, but like they're taking place over a relatively small part of a galaxy. And so sort of the next frontier is expanding outwards from our like galactic backyard to the rest of the Milky Way. And there's a lot of really exciting surveys that are coming online. And one of them is from a space telescope called the Nancy Grace Roman Space Telescope that will launch in late 2026, that will allow us to measure the properties of stars, including young stars, on the other side of the galaxy that basically no one has ever seen before. And so this is sort of part one, but parts 2 to tens and tens of billions, which is the number of stars we'll detect with this space telescope, is still to come.
Yeah, it's a lot like being an explorer, and we've only explored our very local neighborhood, and now we can like go all over the earth, and so everybody's very excited about that. And that's actually what I want to talk about, is just the excitement about this. And so you'll see on the day that the paper is coming out and everything, we'll also release some beautiful figures intended for the public that let you interact with this oscillating Radcliffe wave even on your phone and see the wave going up and down. And why are we doing that? Not because, oh, we're so cool, let us show you. That's not the reason. The reason is because we want people to understand that science, I mean, it sounds totally cliche, but is amazing. And often the way that science is presented in school, especially to students, is, very dry and very rote and very formulaic. And I hope that people get from this podcast that is not, there is no scientific method. Joao came to Radcliffe to work on something that turned out not to exist. Okay, he and Catherine sat there going, "Ooh, how about the next one? Ooh, how about the next one?" Not, "I have a hypothesis that there will be a large oscillating wave in the local arm of the galaxy." Like, that was totally not how any of this happened. And most science is like that. Somebody has an idea. That idea often turns out to be like a little bit wrong, but along the way they discover something else that's really interesting, and they work together as a group, and it's fun. And so I hope that we can convey that science is this collaborative, fun process that, of course, also leads to beautiful pictures and new discoveries, but we want to just pull a spice out there in the reputation of science.
I love it. I mean, it does sound like a very creative and collaborative process.
The collaboration is, for me, critical. I remember showing images that I was working on to Anna von Mertens, and then she would only pick on the corners of the image with like horrible, noisy patterns that was like, who cares about that? Forget about that. And so this is just an example of how, an artist looks at things that the scientist does not. And you can learn from each other in a way that I truly believe at the very, very bottom, we're probably trying to address the same fundamental question, with just very different methods. But I found it so inspiring to, have the goggles of the artist and looking at my own work. And that this is probably my biggest lesson from spending a year having these wonderful lunches and looking, working with my colleague, with my cohort. Just see more. Why wouldn't you see more? Why would you limit yourself to your narrow band that you know very well? You know better than anyone this little tiny part of the spectrum. But the spectrum is huge, it's infinite, and then you just have different ways to look at it. And without, of course, abandoning the scientific method, which is, I think, the way I was formed. The same thing an artist will not abandon the way, in their case, she was formed, where she comes from. And we really can see more. And I think this is fantastic. And this is something actually would only happen in Radcliffe, by the way. You can do things you cannot do alone. I could not have done the discovery of the Radcliffe Wave without Catherine, without Alyssa, without being being really at Radcliffe, given the time, isolate my mind from everything else, and having an excellent student in back then in Catherine. So collaboration is absolutely critical, I think, in science. I think this is friendship, obviously, too, but I think it's I think this is the trick. Just communicate, try to explain, and this I learned in Radcliffe. I had to explain what I did to people that have no clue what a star is or a galaxy. And by doing that, you kind of realize that, we're all together in this thing, and we're just going around the Milky Way, kind of in a dancing. And oh, by the way, and you know how we go around the Milky Way? Just like a dolphin on the ocean. Porpoising, when they go up and down. Mm-hmm. That's exactly how we're going around the Milky Way. Isn't that amazing?
Just the sun, he means.
Well, we're attached to the sun, so we're going also.
But not the Radcliffe Wave, to be clear. I mean, maybe also, but he's talking about the
meaning
sun.
we people.
Yeah.
We right now.
Yeah.
So I think if I had to end with something, I would say collaboration, friendship, fellowship, and this absolutely wonderful institute that made it all happen. Radcliffe Institute. So it was great.
Thank you so much, Joao. Thank you, Alyssa. Thank you, Catherine. Thank you, Ralph. Thank you all so much for telling us all about this new discovery.
And blowing our minds.
That's
and
right.
Congratulations.
Yes, congratulations.
Yeah. We look forward to future discoveries.
There might be some.
Stay tuned.
Born Curious is brought to you by Harvard Radcliffe Institute. Our producer is Alan Grazioso. Jeff Hayash is the man behind the microphone.
Anna Song, Kevin Grady, Marcus Kanoki, and Max Doyle provided editing and production support.
Many thanks to Jane Huber for editorial support. And we are your co-hosts. I'm Evelise Estrada.
And I'm Heather Min.
Our website, where you can listen to all our episodes, is radcliffe.harvard.edu/borncurious.
If you have feedback, you can email us at info@radcliffe.harvard.edu.
You can follow Harvard Radcliffe Institute on Facebook, Instagram, LinkedIn, and X. And as always, you can find Born Curious wherever you listen to podcasts.
Thanks for learning with us, and join us next time.